Hi guys, welcome to our very first video in Unit 3. Andy's here with me to talk about force. To start off our discussion on force, we're going to talk about Newton's first law of motion. Newton actually came up with three laws of motion that we're going to be studying over the course of this next unit. Isaac Newton, that's his full name. He is really one of the founders of physics, and a lot of the stuff that he came up with back in his day was revolutionary. And most scientists of his day disregarded a lot of his theories at the time because they felt like it contradicted what they knew about the world around them. And we're going to look into why they disagreed with this particular law here in just a little bit. So his first law of motion states that an object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an outside force. So this law really has two different clauses, okay? It's got a statement saying an object at rest, that means it's not moving, so its velocity is 0. So this object that's not moving, it's going to stay that way, okay? It's going to stay at rest, it's going to stay not moving. So if an object with a velocity of 0 is going to continue having a velocity of 0, that means that its velocity is not changing, right? Obviously. And so if its velocity is not changing, that means the acceleration is 0. So he's saying an object is not going to accelerate when it's not in motion. It's just going to stay the way it is. And he also said, and this is probably the more revolutionary part, is that an object that's in motion, okay, it's got a constant speed. And here, here they say velocity does not equal 0. So it could equal a number, any number. It could be 5, it could be 15, 25, whatever. If it's at this certain speed, it's going to stay the same speed in the same direction. It's not going to change direction. It's not going to change speed unless an outside force acts on it. So if we're at a constant speed, we're not changing speed, that also means our acceleration is 0. So here's what he's saying. He's saying an object that is standing still will continue to stand still. An object that's moving is going to continue to move forever. It's not going to slow down. It's not going to speed up. It's not going to change its direction. It's going to continue doing the same movement unless it's acted on by an outside force. So let's talk a little bit more about what that means. Here's another example of Newton's law in our everyday life. Suppose that you fill a baking dish to the rim with water. So here's a pan, okay, and you fill it all the way to the rim with water, okay? Meaning if you move a little bit like this, it's going to spill, okay? And you're carrying it, and you're going to walk around a track like this. Okay, you're going to see how fast you can walk around this track holding this baking dish of water. Based on Newton's law, the water is going to spill in 3 separate situations. It's going to spill when you're starting at rest right here and you start moving. Okay, when the container was at rest and you attempted to move it, the water is going to spill. He also says that if you're moving in one direction like this and then you change direction, it's going to spill. The container moving in one direction, when you to change it, the water will also spill. And then lastly, right here at the end, when you're in motion and then you stop, okay, you stop your race, you're done, the water will spill again. Water is going to spill in these 3 situations because the water is going to continue doing what it was doing, okay? So here the water was at rest. So it wanted to stay at rest. So here's your water. When the container moves forward, the water wants to stay. The water's not going to move forward with the pan. It's going to stay in its same spot. So when the pan moves forward, the water ends up spilling out. Same thing here when the container was in motion and you stopped it. Okay, the container right here was moving and the water was moving. Both of them were moving, and then the container stopped moving. Well, what did the water continue to do? It continued to move, so it spilled over the container when you stopped. And the same thing, when your container switched direction, your water continued going the same direction, and so it spilled. So let's look at an animation of this so that you can see a little bit better what I'm talking about. In this example, there's a truck that has a ladder on top of the truck. and the ladder's not secured. When the truck hits the small car, the truck stops because the small car is an outside force stopping the truck. But there's no outside force stopping the ladder, so the ladder continues to move in its same direction, forward. Here's another example. Here's a person who's not wearing a seatbelt. The car crashes into the wall. So the car stops moving because the outside force, the wall, stopped the car. But the person continues moving because there's no outside force, there's no seatbelt in keeping him in his, keeping him in the car. So he's continuing in the same direction with the same speed. Why is this? Why do objects continue to go the same way that they've always gone? Well, that's due to something called inertia, and I unfortunately just drew all over my definition. But inertia is the phenomenon that objects resist change. They want to continue doing whatever it is that they're doing. These are some more just regular examples of inertia. When you're riding on a descending elevator, okay, and your whole body's going down, when the elevator stops, all the blood rushes from your head to your feet. Why? Well, because your body may have stopped moving, but the blood inside your body wants to continue moving the same direction that it was moving, so it moves downward. Another example is when you have a hammer. Okay, here's your hammer, and you want to tighten the head of the hammer onto the wooden part of the handle. You can slam the wooden part of the handle onto like a table, okay? And so the handle stops moving, but the head part of the handle wants to continue moving. So the head part of the handle continues moving downward even when the handle is already touching the table. So it tightens the head of the hammer onto the handle. Same thing when you're trying to get ketchup out of the bottom of a ketchup bottle. You thrust the ketchup bottle downward with a lot of speed, and then you stop it. So the bottle stops moving, but guess what? The ketchup inside still moves downward, hopefully out of the bottle. So these are just some normal, like everyday examples of inertia. However, the reason why the people of Isaac Newton's day did not maybe fully understand what he's talking about is because they saw that when they put an object in motion, when you push an object in motion, it slows down and it stops moving. It rolls to a stop. So they were thinking, well, Isaac Newton's theory doesn't make any sense because when I roll a ball, it doesn't keep moving forever. It eventually stops. And so they thought, how does the object resist change if it rolls to a stop? Well, in comes a new concept. Thankfully, Galileo helped us to figure out this concept. It's the concept of friction. Friction is actually a force. And this force is what makes objects stop moving. Here's our physics book, okay? And if I pushed it this direction, it's moving this direction. Why does it eventually slow down? Well, it says right here, the force of friction acts on the book to slow it down and bring it to rest. So friction actually goes opposite of our movement and slows it down. So there's two important concepts here. First important concept, sorry I sound so bad. I'm like so sick. So my voice sounds terrible. The first important concept is that force is not needed It's weird, my pen was being weird. Okay. Now that might be contrary to what you think. We're talking about in a perfect frictionless environment where there's no friction, force is not needed to keep an object moving. The object will continue moving forever. And I should put here in a frictionless environment. I don't know what is going on with my pad. Normally it doesn't give me this kind of trouble. Okay. The second important concept is that force is needed to slow an object down. So, for example, if I have an object and I'm pushing it across my table, a force is needed to slow the object down, and that force is friction. So now we're going to talk about something that I mentioned earlier, and that was balanced forces versus unbalanced forces. Here's an example of a person, and he's standing on the floor. So here's the floor, and he's not moving, right? He's not moving up, and he's not moving down. And that's because the forces on this person are balanced. The person is exerting force on the ground due to gravity. Okay, this is the force of gravity being pushed downward. However, if this was the only force at play, the person would actually go through the floor, right? But the person doesn't go through the floor. That's because the floor itself pushes back on the person. This is called normal force. Normal force is the force of whatever the object is standing on, it pushing back on the person. So the only reason the person doesn't go through the floor is because the floor, the normal force, pushes back on the person just as much as the person pushes back on the floor. Now let's look at this book. The forces acting on the book are not balanced. Okay, so here's the book. The book is pressing down on the table due to gravity. Okay, and the table is pressing back up on the book, and that's our normal force. And then you are standing right here, right? And you push your book. And so this is called applied force. When there's a push, it's called applied. So here the forces are not even. My force going up, my force going down, they equal each other out. Those are balanced. But my force to the left is unbalanced. So it moves. So that's really important. If your forces are opposite of each other like this, and they're of equal value, there's not going to be any movement. If there's a small force this direction and a really big force this direction, that's called unbalanced. Unbalanced forces always cause motion. So let's look a little bit more into the math side of this concept force. Force can actually be measured, and it's measured in the unit called the Newton. Okay, so this is the unit of force is a Newton, which we show with a capital N. A Newton stands for 1 kilogram times meters per second squared. What it's really standing for is a Newton is the exact amount of force it would take to move 1 kilogram of an object and accelerate at 1 meter per second squared. Okay, force is basically like acceleration. So it's the mass of the object times the acceleration is your force. So, I don't know. Okay, there's a lot of different types of forces, and I've talked about a couple of them. The normal force is always the force of whatever the object's sitting on pushing up. Okay, so the normal force is always the force of like a table. So it's like an upward force of whatever the object is sitting on. Okay, so it's upward force of whatever the object is sitting on or resting on. Okay, and normal force is pretty much the only force that's always in the upward direction. All right, frictional force is always going to go against movement on a surface. So it's always going against the direction of movement on a surface. So for example, if I have an object and I am pushing it this direction, the friction's always going to go opposite. So friction force always goes opposite of your push force. Your push force is called your applied force. That's right here. This is the push force. And even though like I might be standing right here and I'm pushing the object over here, your arrow always needs to go away from your object. So don't draw your arrow like this. Don't draw it like pushing like that. Take that arrow and move it to the other side and draw it like this, okay? Okay, tension force is the pull force. That's if here's an object and you're holding it by a string, okay? The pull force right here that's pulling it upward is your tension force. Let's see, what else have we not talked about? Air resistance. Okay, air resistance is if you're dropping something or throwing something. Air resistance will always go opposite the direction of movement if it's thrown. So it's only, air resistance is only important to us really when the object is being thrown, okay? So here's my object, okay? I threw it this way, okay? Here's my applied force this way. Air resistance is always going to go opposite. Air resistance show with AR. An applied force you can just do with an A. Spring force is similar to a pull force, but it's pull force specifically of springs like these. It's only if you're holding something with an actual spring. So it's of a spring. And then we're not going to do a whole lot with electrical force or magnetic force right now, but gravitational force, you need to know, is always, always, always pointing downward. Okay, because it's always pulling things downward, in the downward direction. Okay, so now let's go ahead and apply this to some problems. When we draw an object and we label all the forces that are happening with arrows, we call this a free body diagram, okay? You first have to show the system, which is the object that is encountering the forces, and then you need to write down all the forces that are at play in the environment around it. Remember I said normal force always points upward. That's if the object is sitting on something. Gravitational force always points downward. Applied force is when it's being pushed. And remember how we said friction always goes opposite. So friction is opposite of the push. So let's do some actual problems here. Okay, a girl is suspended motionless from the ceiling by 2 ropes. Okay, so I always draw my objects as a box. So the girl is going to be a box, all right? And she's suspended in the ceiling by 2 ropes. So if she is being held in place, we know gravity is at play, right? So here's gravity. Gravity's going down here. Force of gravity. But she's not falling downward, right? She's being held in place. That means something must be doing an equal and opposite force in the other direction. And it's 2 ropes, so I'm actually going to draw 2 arrows. This is the force of tension. Okay, because the rope is causing the tension. And that's it. There's no friction at play because it's not being moved. There's no air resistance because it's not being moved. And there's no push happening. So this is the only drawings I have to include. Okay, here an egg. Here's the egg. It's falling from a tree. If it's falling, I know it's going downward due to gravity. If it's falling in the air, I would need to draw air resistance in the other direction, but here it says neglect air resistance, so don't worry about air resistance. Then these are the only forces at play. Okay, there's no friction because it's not on an object. There's no normal force because it's not resting on anything. And there's no tension or applied force. Let's do another example. Here's an object. A rightward force is applied. So we have an applied force in the right direction. That's applied to a book in order to move it across a desk. Okay, now this makes things more complicated. Here's a desk. We know that the normal force of the desk is going to push up against the book. So here's my normal force because it's resting on something. Gravity pushes the book down on the desk. These two will equal each other out. The applied force is going forward. It says don't worry about air resistance. And it says consider friction. So if it's being pushed in this direction, friction always goes the opposite direction. So here's the force of friction. And one last example. Actually, I think it's the same example we just did. Yeah, it's the same example, so don't worry about it. Okay, next I'm going to add in actual numbers of force because the amount of force that's included in each of your arrows makes a difference. Okay, here's your table. The table is resting on the ground, so the table is, let's say this is the table here. The table is pushing down on the ground due to the force of gravity. The ground is pushing back up on the table. That's called the normal force. The boy here is pushing in this direction, so this is the boy. The force, the applied force of the boy is 100 newtons. The applied force of the girl, she's pushing this direction, is also 100 newtons. So this object is not going to move. Why? Because we have balanced forces. We know gravity and the normal force are equal and opposite directions because the table's not moving upward or downward, so they must be equal. The table's not going to move left or right because their forces are equal and opposite. His force is 100 newtons to the left, so it's technically negative 100 newtons. And her force is 100 newtons to the right, so it's technically positive 100 newtons. And so they equal each other out. However, in this example, the girl is going to push with 200 newtons this direction. That's to the left. And he's going to push 100 newtons to the right. And so we can see that our net force here is going to end up being 100 newtons to the left. That's the amount of force that the book is going to move with. Okay, this is unequal or unbalanced forces. So unbalanced forces means movement. Okay, the table will actually move. We'll talk more about net force later. What I want to do now is I want you guys to practice drawing out these free body diagrams and calculating the net force of the object and where it's going to move. For example, here's an object. This is the force of tension, so it must mean it's being held up by something, okay? And it's being pulled. Tension is a pull force. It's being pulled with this much force, but gravity is pulling on it with this much force. They're not equal. Even though they're opposite, they're not equal. So I can subtract them, okay? And I can see that here's my net force. It's going to be pulled upward with this much force. That's how much is left over. If I look in this example, the air resistance is pushing against this object with 600 newtons, but gravity is pulling the object with 800 newtons. So if I do my subtraction here, I get negative 200 newtons, which means it's going to be pulled downward with 200 newtons of force. Here I can do the same thing. When there's three different forces, you need to do the up and down force first and then look at the left and right force. Here the up and down force are going to equal each other out. 50 minus 50 is still 0, so it's not going to move up or down. Now let's look at my left and right force, okay? Here I know I'm going to be moving with a force of 20 newtons to the left because there's no other opposing force. These are more examples here. 1200 minus 800 would give you 400 newtons in the upward direction. Here, what's our net force? Well, as you can see, it's 200 newtons down, and this is 20 newtons to the left. So these are the same problems, it's just the answers for them. And that is it for our video. You may do your sample practice problems, and I will go over the answers on Tuesday. You guys have a great day, and hopefully my horrible voice didn't ruin the video for you guys.